Okay, so we have one final way to represent electron configurations, and it's called orbital diagrams. It's the same idea as the electron configurations. We're just drawing it instead of writing symbols. So the electron configuration for hydrogen that we had from before is 1s2. So in order to show the 1s energy level, I just draw a box and I label it 1s. And each shape can hold 2 electrons. So in this case, I've drawn the electron pointing up. You could also have drawn it pointing down, because it actually doesn't matter since there's no other electron in hydrogen. Oh wait, no, it's not 1s2. It's 1s1. I was getting ahead of myself. Helium is 1s2 because it has 2 electrons. And now I can't point them both in the same direction. They are both in the same box. They have to be pointed in opposite directions. It's kind of like shoes. If you have a shoe box, the two shoes can't point in the same way because then the box doesn't close. So we have to point one up and one down. It doesn't matter whether I draw it in the opposite direction or not. They mean the same thing. Now lithium is the same thing, but we have one more electron, which is in a new period. It's in the second energy level here. So I would draw the first one the same way, and then the second one I could point the arrow any direction that I want. Okay, so here's our hydrogen. I'm just going to point it up for convenience sake, but you could choose any direction you want. Carbon has the same one. Well, let's do the diagram here. It's 1s2, 2s2, 2p4. This is from before in our notes. So 1s2 is shown by drawing one arrow up, one arrow down, and I shortened them to half arrows because I sort of have limited space here, but you can draw it however you're comfortable. The 2s is also full, so we draw 2 electrons there. And the 2p has 3 boxes because it has 3 shapes. They're all the same energy level, so these electrons are going to spread out until they really don't have a choice anymore. So we draw one arrow up in each box, or you could draw one arrow down, it doesn't matter to me. And then your fourth one has to pair up with one of the other arrows. Okay, so nitrogen has the same configuration but one more electron. So 1s2, 2s2, 2p5 is what nitrogen has. So we can draw the same thing here. 2 1s electrons, 2 2s electrons, and then they're all going to point in the same way until they can't avoid, same way in different boxes, until they can't avoid pairing up. So this nitrogen has one unpaired electron in the 2p orbital. Wait, no, I messed up something. Hang on. Oh no, this is what I get for not looking at my periodic table. So carbon has only 2p2, not 2p4. Nitrogen is 2p3, and then the oxygen we're going to do in a second is 2p4. So let's fix this. Let's go back to our slides here. This is 2p2, so we have too many electrons. I'm going to take out 2 of these. That's better. Okay, now nitrogen, we said there's one more, so it's 2p3. So I have to remove, I'm going to fix this here. So 2p3 would have 1, 2, 3. Now this is kind of like having children and bedrooms. If I have 3 children and 3 bedrooms for them to be in, they will take separate rooms. So they're perfectly comfortable being all spread out like that. All of the arrows have to point in the same direction, though, because it turns out when they spread out in the same energy level but different shapes, they all match up. They spin in the same direction. Now, we said oxygen is one more than nitrogen, so it would be 2s2, 2p4. So our 1s's are full, our 2s is full. The 2p can't have everybody in their own bedroom. You've got 3 arrows, and so I've got to put one of them in the same box as a different one. So that's the 4th kid, and they just have to suffer by sharing a bedroom. The next electron might go in any of the 2 boxes that are remaining for the next element, on and like that. You just want to make sure that no electrons in the same box point in the same direction. They have to be opposites. That is because these two principles guide us when we were doing electron configuration and orbital diagrams. The first one is called the Pauli exclusion principle, and it says that no two electrons in an atom can be the same. So they have to be different. They have to be spinning in a different direction, or they have to be in a different energy level. Hund's rule says that electrons have their lowest, which means most stable energy when their spinning is aligned. So that means I would point all my electrons up if they all get their own bedrooms. I would not do, so this is good, I would not do, let's do it in red so we know what not to do. So this one's good. This one is what we don't do. I'm not going to put one up, one down, one up, okay? They don't line up that way. It's not stable. Okay, now as we saw in lab, there is a trend in the periodic table. So I want you to open the lecture slides and click this video and watch it. Pause this one while you're watching it. Okay, so what we just saw is that sodium and then lithium, potassium, and rubidium all react kind of similarly. They all explode in water. Now, the farther down the periodic table we go, the more reactive they are. So we saw these two in lab, right? The sodium barely catches fire, but the lithium really does catch on fire and it zips around a lot. If we tested potassium, we would have seen a bigger fire and on like that. The reason they all react the same is because they're all in the same group. They're all in group 1. That means they have similar electron configurations. So if you look at the electron configuration of, say, sodium, it has the core from neon, and then it's 3s1. Whereas lithium, oh wait, that's backwards. I have lithium is first, then sodium. Oh my gosh. What a rough day. Sorry, guys. Lithium is littler than sodium, so it goes first, then sodium, then potassium, and then rubidium. Anyway, so the electron configuration for sodium is neon in brackets 3s1. For potassium, it's going to be argon 4s1. So these both have the same number of outer electrons. They both have one outer valence electron. So as it turns out, they all react the same because they are all trying to get rid of that one outer electron, because when they do, they have an electron configuration similar to the noble gas before them, which is very, very stable. Everybody just wants stability, so that's what they try to do. Okay, so the reason we use the shorthand notation, other than the fact that it's convenient, is because it shows us just the reaction that is actually happening. So when sodium loses an electron, it always loses a 3s electron to have just the neon core left behind. So when we draw shorthand configuration like this, we are showing just the electrons capable of reacting. We call them valence electrons. All right, so I'll do the first one with you, and then I want you in Top Hat to fill in these ones, all right? So we got to go back to our periodic table down here. Well, you can pull yours out. I'm going to clean it up a little bit. And so what we got to do is locate the sulfur we're trying to find. So here's the sulfur. Oh, you can't see that. It's in period 3, right underneath oxygen. Okay, so here's the sulfur. And we're going to travel all the way back to the noble gas before it. So that would be neon. So this one's going to have neon in brackets. And then we count forward. So from neon we go 1, let's see, that's the 3s. And there's 1, 2 in that box. And then 3p, 1, 2, 3, 4. So 3p4. So we're going to put that as our electron configuration here. Ooh, it's a bit big, but that's where it goes. Now the number of valence electrons is just the total of all of my superscripts. So 2 plus 4, 6 valence electrons. Okay, so get out your periodic table and go into Top Hat and finish these. They're going to be individual questions, but you can fill them all in on your notes first and then just answer it on Top Hat.